Last time you ended up with something like you are trying to given a set of examples, so you have some kind of input data and expected output. And your task basically is to find some data such that some error function of the data is small as possible. And we devise a nice analytical solution to that. We'll calculate some metrics, iterate metrics, and everything is fine in the solution, which is a little bit inefficient because it requires a cubic time algorithm, but who cares? It's good, it works, yeah. So there are a couple of questions about this, and we will start with something like, okay, why square error? Why is there 2? So, any opinions why we use square error and not something else?
So the error is always positive.
Well, these are positives, yes. We want like, okay, if you predict something which is smaller than expected, okay, and if you predict something which is larger than expected, we want have a positive error. So there's one reason why to squaring, we will get a error function which behaves as good error function. But why not 3? Why not, okay, 3 is better. Why not 4? Yeah.
What's the solution? Does it get more complex?
Yeah, solution will get more complex. Yeah, that's another issue. So now actually I know about 2 reasons why 2 is a good choice. One reason is that you get a nice solution. You will get derivative which is linear, and out of there you will get a system of linear equations. So we use 2 because it gives us a nice solution, which is quite good. Another reason is that it has a connection with some kind of like probability theory, where basically you don't ask about error function, but you ask about the probability output. So basically, if you look at some kind of like typical distribution, normal distribution, normal distribution is something which is approximately t times something squared divided by some constant. It's a normal distribution. And then you look at that, it gives you some kind of like probability of the output. So you have a normal distribution set somewhere, and it will give you that looks some kind of mean here. Okay, so we have a normal distribution center at some point, and what it ends up is that's okay, it gives you distribution of x. The further away from the central point, it's less probable than this. And the nice thing is that you can look into this kind of prediction as a probability problem to maximize probability of the data, probability of the outputs, and it turns out that basically it's a product of probabilities of all outputs, and if you take a logarithm of them and sum of logarithms, and logarithm of this is just square error. So basically having a squared error function is also equal to some kind of like normality assumption about the data. So the errors follow normal distribution, there are no heavy tails, other random things. So this is like two reasons why we use two. And now what we will do, we'll try to explore other possible error functions. So any idea what error function we can use as a set for squaring the difference? Any idea is good. Sorry?
Absolute value.
Absolute value, that's yeah. Other function. This is actually called L2 norm, so this will be called L1 norm. And what is it? It's basically the error function which uses absolute values. Why the absolute values? Because also gives us a positive result. So the error function behaves as we expect it to do so. The bigger the error function. So it can work. We want to make this as small as possible. Other option can be like this is L2 norm. So this is called. Maybe we can use L3 norm, L4 norm. Nobody uses them actually. The other interesting example is actually L infinity norm. And this behaves in a similar way as you would put like a big exponent there. But if you put a big exponent there, basically the maximum error is only interesting one. So actually the error function would be maximum of all errors you have. So this is like kind of like another error formulation. And why would we want to use some kind of like other error function? It basically gives us a different behaviors with respect to outliers. Because the L2 norm basically, like if you have something which is outlier, it tries to follow that. So for example, when we have a solution like a couple of points, most of them are centered around some line, and then you have like one outlier somewhere around here. The L2 norm would try to deviate towards the outlier somehow. It would be like L2, maybe something less. The L1 norm would little bit ignore that outlier, so you go like this. And the L, sorry about that, the one higher. And the L infinite norm would actually follow the outlier as much as possible, so it will be somehow centered around, I don't know, here. So the one reason why we want to use another norm is basically your data has some kind of outliers in that. It's good to try some kind of like other error functions because one outlier can screw your whole prediction because it just turns it somewhere away. So it's a good idea to try. The question is, can we optimize that? Like, okay, I can have another error function, but if I cannot find a solution, the error function is basically useless. But it turns out that there is a good and easy way how to optimize this. It's called linear programming. And this is basically a big hammer, something you can just use in a form of library. It's available in many programming languages, so it's very easy to use. So first, like a survey question, who doesn't learn anything about linear programming before? Don't be shy about that, it's okay. So, the linear programming is actually nothing to do with the typical programming. It's more of the set of equations and equations. The linear programming is basically you have some variables and basically something in the form like find, for example, ABC such that 2A minus 3B plus 3C is maximized, and it should respect with respect to some condition, like for example, B should be, I don't know, minus 2, A plus D should be at least 5, and A plus 3C should be at most 47. So basically what you are looking for is there are some variables, for example ABC, and you are looking for like solution of those variables. You are looking for concrete values for those variables such that some expression is maximized, and you have some conditions on those variables. And since it's called linear programming, we require that all of these expressions are actually linear functions of variables. So should be linear. It's basically very important. So we are looking for such values that this is maximized and this inequality is home. And then everything should be linear, then we have a linear program, and we can use some kind of library which solves that for us. One of those libraries is called, for example, libraries called this. One of them is called strict. This is like typical solver, but it's basically there are many libraries for linear program solving, and it can be solved in polynomial time, and it's usually quite fast. So the question is like how we can formulate these problems. We are looking for some data, so that we are kind of maximizing those deviations. Minimum deviation, sorry. So the example solution for that is that we can use linear programming, for example, for L infinite norm. We will have another variable which is called the delta, that would be error. We have thetas, which are basically coefficients, the vector, and what we are basically doing, so linear program for L infinite norm. This is a little bit easier. You can use a couple of tricks. So linear program for L infinite norm. So what we are, this is basically the maximum error. So this delta is the maximum error we could get. So we want to minimize the error. That's all it is. We want to minimize the error. And what we want to do is find, we need to have a coefficient which respects those errors. So basically what we want is that C epsilon 1 minus delta less than the predicted like this. Yeah, so okay. This plus delta and so on. Epsilon. Okay, so this is what we are looking basically for. We are trying to minimize this error and minimizing the error, and we want every example to be at most delta from the error.
What are your variables?
Delta and coefficients, the beta.
So that n plus 1 variables.
Sorry?
That's n plus 1 variables.
Yes, and plus one variables. Yeah. And basically, you shouldn't be confused with this. This is like not it looks like not linear expression, but actually this is like a template for the linear program. You should treat those x's and epsilon as a constant. So when you are trying to solve this, you have a concrete instance where you will fill all the x's and epsilon into this program. So when you are giving this to solver, actually every epsilon and x variable is already filled in. So you will put the concrete variables there, and then you have a linear expression in theta and delta. And that's what you are looking for. Okay, and if you want to have a linear program for L1, it's a little bit more complicated because we are dealing with absolute values. It's kind of annoying. Let's start with that. So we want to generate a linear program from L1 norm. So the one we sum all of the absolute deviations. X, Y, theta. So it's kind of a little bit annoying. So what we will do is actually we will have a deviation for each example. So we will have delta y, which is error for each sample. Is like another variable, and it's a positive number. That's one thing. That's something we will have to put also actually here. Because if you don't put the delta here, I think maybe. Oh no.
Okay.
No, that's okay here, but not, it will be not okay. Okay, so this is error for example. But again, what we want to do is find vector of deltas, vector of thetas for each vector of deltas for each sample, vector of thetas for each attribute. So we minimize the sum of errors. We want to minimize the sum of errors, which is good. We also require that each error is a positive one. And what we do a little trick with absolute value, because when you play with absolute value, it's not a linear function, but it can be solved with a couple of inequalities. And it looks basically like this, that we say that for each variable.
I think it's also implied with delta I is non-negative.
Maybe yes. I'm not completely sure. Like, it doesn't hurt to put this condition in, and you'll have you when your output is negative there. Yeah, but yeah, it shouldn't. Yeah, this implies. Sorry. Yeah, so the idea is basically that you have an error, for example, you're basically, the difference shouldn't be bigger than this error, and this gives you like pounds for each. And we want to minimize the sum of the error. It's a pretty simple one, kind of works. sometimes we use it, but why we actually talking about linear programming is that it will be used in a context of support vector machines where we will build a bigger programs. So again, when we are back into this, we see like three kinds of norms. Basically, I haven't seen the L-infinite norm in any practical usage. Sometimes I use L1 norm when I have some problem with outlines, but by default I probably use the quadratic norm like 99% of the time, right? Because it's like default choice which is basically like simple to use and works out of the box. The L1 norm sometimes is a little bit tricky. So the next thing which we should talk about is like other optimization options. Because what we see is like basically analytical solutions, we see linear programming, and then the one big area of optimization, and actually one we will use most of the time, is numerical solutions. Optimization. Where you don't care for the exact formula of the result. You don't care for the exact formula for data that multiply these two matrices inverted and so on and so on. You just care about the result. So numerical optimization will find you the best result up to some precision. So and there are actually two courses in our university which deals with this, at least two courses. One is called, it's for financial mathematics. Oh, yeah, it's for financial mathematics and it's called free optimization methods. That's something you can attend. It's taught in summer. And the other course is actually taught in the winter semester. It's for applied informatics and it's called multidimensional analysis and numerical mathematics. And these are like deeper courses about numerical optimization. We will always give the basic ideas. So the idea here, what we are taking mostly, is that we want to find the minimum of some function. So we are given a function, find its minimum. So it basically looks like a function, my little quirky, okay, this one is not so quirky. And what we are trying to do is we want to try the minimum of this function. You don't care about like exact value up to like a million digits. You just want to find its minimum up to some reasonable precision. So you start at some point. And what you do, you basically look at the derivative of the function and move down the slope. It will send you somewhere. You look for a derivative and it will send you somewhere. Then you again look for the derivative and it will send you down, so on and so on. So this is like very difficult method. It's called the gradient descent. And the main basic idea is that start with some initial solution. So theta for simplicity. And update the convergence. So how do you update it until convergence? We just said the new theta is theta plus some step, and here you take a derivative of the error function. Respect theta, and here should be a minus because you want to go down small. I hope I wrote it in the right way. Yeah, wrote it. Another way how to draw this is, sorry. This is probably how you read it. So it is basically like update. You always look for the gradient and you move down slowly the gradient. Like in a one-dimensional case, it's basically you are moving down. If you want to imagine like multi-dimensional case, like imagine that you are on the hill in Haida rather than how do I go down regarding the volume? So the gradient gives you the direction down the volume. There are multiple directions which will lower the error, but the gradient is basically the steepest direction down the volume. Like it basically, if you have this kind of like, if you visualize the function as some kind of like, this is the volume, this is the lowest point, and you are trying to go down. So when you start here, the gradient will slowly send you toward the minimum somehow. So it always points in the steepest direction down below. But this is basically a gradient distance algorithm. The only problem with gradient distance algorithm is this. This is called the step size. And basically, it should be set up either manually or with some heuristic which should slowly slow down. There are many ways how to set a step size actually. So that's why I refer to other courses. In practice, what we do, we try several values of the step size, and when it works, we are happy. So you start with something, I don't know, 1. If it blows up, you lower it. If it still blows up, you lower it. And when it will start working, you will use that step size. So this is basically trivial gradient distance algorithm. The problem with this gradient is actually there is a small problem with that. When you have a lot of data, like we are talking about millions of data points, we are taking the gradient over the whole data set, which is kind of annoying because you do one small step and you have to use the whole data set for that, which kind of like it's maybe unnecessary because maybe if you just check part of the data set, it will give you a good idea how it should move. So we take this idea to the extreme that we will always say that, okay, I will only use one example, and it will tell me where should I move. And after going over many examples, I will arrive at a good point, but maybe I will be faster because I will not have to spend for each move, I will not have to go over the whole data set. So gradient distance means whole data set for each update. Which is set and slow. So the idea is called stochastic gradient distance. And the idea is that you will update after each cycle. So how it looks like, basically, we initialize the theta vector. It's a kind of default initialization. When we are solving linear problems, even zeros are good. When we are working with a neural network, zeros are not good. We will see in the next questions. So we will initialize the theta and repeat, I don't know, either until convergence or until some kind of threshold for epochs, so that's the until convergence. Or, as I said, until I am patient enough to not press Ctrl+C to start the program. That's up to you. So we will repeat this until convergence for each sample. Now, let's have a one important line here, sample samples. Each sample do an update. This update will be very similar as before, but we will only take a gradient for one sample, so I will do it. I will try to show you how we do it. Let's say, let's call it JY. Error on one sample. And this is basically, the stochastic gradient distance is kind of like the default go-to algorithm whenever you solve basically any problem in machine learning. Whenever you are able to formulate a problem like optimize this error, you will end up with stochastic gradient descent of some kind of like small derivation. And even in this kind of like linear regression setting, when we recall the derivatives which we have, derivatives are like stupidly easy. It's basically an error on one sample, and for each attribute is basically just like value of the attribute. So if you recall, like try this. Down, so the derivative of the attribute with index j is basically for on the y example, this is for linear regression. And for linear regression, what you have is basically this difference. You should move it, multiplied by the value of the x. It's like this negative minus. Basically a very simple sort of like a formula which you can use to calculate the error once propagated for each sample. So it is kind of like easy to code, easy to do, it works quite well. The actual variants which some people use with the stochastic gradient descent, there are like a couple of variants in literature which you can find. And this is like the keywords to look for if you work with stochastic gradient descent doesn't make you happy because it's slow or something like that. The one keyword to look for is momentum. It's sort of like it's like physical simulation of rolling ball down the body. The steepest direction gives you acceleration, the ball maintains some velocity and it moves based on that. It will help out in some cases. The other keyword is other, kind of like a little bit more complicated. And the last thing which doesn't basically work with stochastic gradient descent, but it's like a big hammer if you want to optimize something. And this is popular mainly between mathematicians. So LBFGS, this is like the ultimate hammer. So these are things you can look for if you want to do some kind of numerical optimization and finding the minimums of functions. Yeah, so this is basically like how you can do optimization in context of machine learning. Yes, there are other methods. Somebody can, for example, ask like, what about, I don't know, simulated learning in genetic programming, I don't know what. You can use them if you want, but usually they are not always so efficient. Like, even like the gradient descent has a property that if the function is convex, it will find the solution. But if the function is not convex, it's multiple local minima and so on. The usually gradient descent leads to faster solution than any of like heuristics like simulated learning. So it's always a good choice. But if you end up in some situation where local minima are a problem, maybe simulating learning would be good. In many cases, the gradient descent is a nice thing. You should use as a default. Okay, so what's next? Next thing is we started with linear regression, which linear regression, as it goes, it's only linear, and sometimes you can have complicated dependencies between your input and outputs. So, for example, we would love to have some kind of like polynomial dependency. So, let's answer the question, what about higher order dependencies or interactions? So for example, we have two input attributes. So maybe our model should look like this. Maybe our model should be like, I don't know, epsilon is something like theta 0 plus theta 1 times x1 plus theta 2 x2 plus theta 3 times x squared plus theta 4 times x1 times x2 plus theta 5 x2 squared. This is like all possible higher order things up to 2. So also know that we can multiply our attributes between themselves. That's also kind of like a second order polynomial max. So maybe this should be our model instead of the linear model. Okay, and the question is like, okay, this can be called polynomial regression. But actually a name for that is polynomial regression. You can have even higher factors, then you can also go to like surveys, polynomials, but I'm lazy for that, I don't want to do that so much. So the question now is like how to solve the polynomial regression. And there are two ways. One way is you repeat everything we did for linear regression. So we will develop some equation, solve them, figure out that we should multiply some matrices, and maybe inverse them, and then we figure out, okay, we can just gradient descent. everything will work here actually. But there is one much simple solution that we can use. We can actually use linear regression for solving polynomial regression. So that's kind of quite an idea, and who knows how to do this? Who has an idea how to do this? How to use linear regression to solve polynomial regression?
Maybe we say that x1 squared is a different variable.
Yeah, exactly. So the idea is that if you look at this, and if I just rename this kind of thing, I will call this an apple, this would be an orange, and this would be I don't know what, it would be a pear. So you can forget that there is like x2 squared. It's just like a new attribute. So the general idea here is that, okay, you'll just transfer the x, create your attributes, and you'll solve linear regression. Because if you forget that these kind of things are like higher order polynomials, it's basically a linear regression. So maybe not forget about polynomials, just transform the input. So instead of x1, x2 as an input, we will use x1, x2, x1 squared, x1 times x2, and x2 squared. And then we'll do this transformation for every sample we have, and it will just work. The solution is basically the same. We'll solve the linear regression, and we will have this and use linear regression of that. Nice. And we can go even further with this, like we create some new attributes, like an attribute and multiply some inputs together. And what I can actually do is I can go even further and use basically any function there. So I can generalize this, use any function. Very popular choice, something which I recommend. Logarithm of x plus 1. So if you have some kind of like positive input or non-negative input, sometimes it's kind of like the attribute goes from like sometimes it's 1 to and sometimes it's 1 million, and your linear regression refuses to fit. So just take a logarithm of that. So this is like one function we'll use. So we will use any function. And basically, we will transform x into some kind of closed function. We will use multiple functions. Theta, k. So what we we want to kind of maybe change some attribute to 1, we can just basically create some functions and transfer our input into something else and use linear regression on top of that. It nicely works, actually, and there is sometimes some people call this feature extraction. People call this extraction. So we extract some features from X. And when you think about it, that X doesn't even have to be vector right now because it's just a function. So X can be a string, X can be an image, X can be some DNA sequence, it can be anything right now because we have just some functions which extract values from the domain. So right now this can be actually an object. So as a typical technique in machine learning that will transform some object into some values. And those things can even be like identity functions, those things can be polynomials, those things can be logarithms, it's up to you. That's basically anything is good, and then you can just feed it into linear regression, and you will get something which maybe the actual, like maybe one question here is like, okay, well, I have, let's say, I have 1,000 training examples. So what? I have 1,000 training examples here. What I can do, I can maybe create 1,000 features, even more features, 2,000 features. And let's say I create 1,000 features out of those 1,000 training examples. Then I can probably fit the linear regression precisely on top of those samples. So I will get precise fit, it can look like this. Use many features, get precise fit. This. Are we happy with this function? Do you want your prediction to be like this, or do you want your prediction to be something else? That's the question. So, are we happy? I'm not happy with that. And we will touch it actually in some next lecture. This is just like a teaser that maybe if you overuse your feature extraction, you will get something that is weird. Doesn't follow natural laws. Like magic. No, okay. One more idea actually before this generalization and this feature extraction. What can be an idea like logarithm of something is lambda delta. The second good idea is like local function, local basis function. And it is basically just like a distance from some point in space. So your data function will be on the regress x, will be just for example something like that. Maybe divided by something. So it's a distance from a point in space. It's kind of like also with an exponential usually, so more further you are from the point of model gets. And the basic idea is that you want to give some kind of like weights to some places. So, for example, like if you have some place here, the weight is actually like that. If your example is clothes, to the center, the value will be higher. If it's farther from the center, the value will be lower. And you have multiple centers like this, and you can probably pick up function over there. Just an idea of what to do. And one last trick for this last thing. There are like multiple tricks like this, sort of like. One thing which I personally think that it's just a nice trick, and some people think it's very nice trick and should be asked in state exams. So, I'll show it. The name of this trick is actually called locally weighted regression. And the idea is like this. For example, suppose that your data isn't linear. Maybe it's like this, or maybe it goes down. So there is no chance that you can use a linear regression in this scenario. Maybe you can use polynomial regression, but this is sort of the other way. Like the idea is that we will use something which we will call the weighted regression. And the weighted regression is just a normal linear regression when each sample has a different weight. So weighted regression means that there is a weight for each sample. So maybe some samples are more important than others. Okay. And then our error function is very similar to previous ones, but it will have weights there. So you can basically make weighted something out of anything. You can have a weighted network, so you can have weighted regression. You can assign weights to samples in any kind of setting. Sometimes just by oversampling, sometimes just by using weights. Okay, and what's the idea in locally weighted regression is that, let's say I want to predict, okay, I will just spread this picture a little bit more. And suppose I want to predict something around this point. I want to predict here. Let's call this point some x 0. This is where I want to make a prediction. And actually, how the idea of locally weighted regression is that, okay, I care about these samples around me. Yes, I care about them. Do I care about this guy? Not much. So the idea in locally weighted regression is that, okay, I will calculate, I will solve the linear regression every time I want to make a prediction, which sounds a bit silly, but that's idea of locally weighted regression still. So I will assign the higher weights to the nearest point. So linear regression every time I want something predict. Yes, I'm serious with that. When I first saw this, I was like, maybe somebody is joking, but no, it's like this. And assign higher weights to the samples. And the formula we can use for that is actually basically the one I already shown a couple times. It's the distance point divided by something. And the only two things you can have there is basically this guy here. So the guy here basically gives you like, okay, if the sigma is small, you really give a lot of weight to the samples. If the sigma is large, you give also some weight to the samples which are further back. And basically that is right. There is not much that can be said about this. You assign weight to samples, also with linear regression, get one prediction, and move on to another sample, solve linear regression, and so on and so on. Basically, the only thing which you should work out at home is basically how will the analytical solution change when we give weights to every sample. How this change solution. It will be basically just multiplication with some diagonal matrix, so it's nothing hard, but this is something you can do for your homework. It's very easy. So it is one way how to maybe solve a nonlinear problem, just do something local. Sometimes it works, you try it as well. Okay, so and actually, when I'm thinking about this is actually this idea is not so silly when I'm thinking about it right now, because right now, like the whole machine learning field is connected to deep learning, and then everybody seems like, okay, deep learning is white box. How do I understand what neural network is thinking? And there is a system called Line. I don't know what it exactly means, but I can check it out. And Line is not the thing you put in your computer. Line is actually okay, we will figure out the application soon, but the idea is that you want to explain a prediction of your model at some point, and you will use just some kind of like big complicated model like, I don't know, it is a big network, so you cannot explain like why you use some kind of weight somewhere. The classifier is complicated, but it's kind of like what you can do is basically take your prediction at some point and run locally weighted linear regression there, and you will get some kind of like weight for each attribute. So Line uses locally weighted linear regression for explaining predictions. Locally interpretable model agnostic explanations. So this is something you won't maybe appreciate that now, because you just see the linear regression was to explain that. There are more complicated machines which you construct, and this Line is sort of like a toolkit which will use this kind of locally weighted linear regression for explaining like what your model does at that point, like what it finds important and what's not so important. So this is sort of like a framework you can use. So that's basically all from our lecture. So what we see is like three important things. I think first important thing is that there is some kind of like a gradient descent which you can use for solving basically anything. The second important thing that you can extract features from your input vector and convert it to something else and treat your classifier, and it will give you also polynomial regression. And the last point is that this locally weighted regression is actually not so silly as it looks. That's all for today's lecture. Have a nice day.